So I like to start with how we look at patients, and to remember this from Jeff Bland, that we are a composite of multiple systems, and pay attention to the web of the things that interrelate all these factors together. So very rarely is a person one problem. You very rarely find a person has zinc deficiency and that's it, right? Usually they've got some mechanical problems, they might have emotional problems, they may have dietary problems, hypersensitivity to certain foods, they may be short of probiotics and so on. So don't forget to look at the whole, and that's the beauty of the eye positions and the accessing when you put the body or the eyes into distortion, that you can access different departments. And the beauty of it also is that it comes out in an order of how to prioritize which one to deal with first. So a person may have a mechanical problem, but it may not show up initially because they need some zinc or they need to get rid of their parasites, etc., which is then the cause of the muscle getting weak, which is why they develop the low back problem. Okay, so there's a chain of events, and the eye positions will help you to determine which ones to do first. So follow the words of Jeff and pay attention to the interrelating factors. Okay, never look at it just from a single point of view. That's the job of the specialist, isn't it? You know, the specialist in the medical world looks like this, and no specialist likes to get into the domain of another specialist. They all like to have their own speciality. So you go and see an orthopedic person for a bad back. You don't go to a neurologist or a rheumatologist. But if you go to an orthopedic surgeon, he's going to probably recommend surgery, because I don't be surprised about that. Okay? Whereas if you come to see an osteopath or a chiropractor, they're probably going to suggest mechanical treatment, and they're not going to suggest surgery, okay, unless all else fails. So remember that specialists are people who only look in the one direction. And we have the beauty to be able to look in multiple directions and bring that web of interrelating factors all together. So the first thing I want to just introduce today is the principles behind using nutritional medicine, or functional biochemistry, as I like to call it. And one of the most important things that we deal with, which we can excel in, is how to assess enzymes and enzymic reactions. So the body is full of enzymes and enzymic reactions which change certain things from one substance to another. So enzymes are proteins. So that's the first thing you need to remember. An enzyme is a protein, and it is part of a genetic expression. So what the genes in our cells encode for are proteins. Now, not all proteins are enzymes, because we use proteins for building muscle and tissues, but all enzymes are proteins. Therefore, when there's an enzyme problem, it's a reflection of the expression of the gene. Okay? So either the gene is not being expressed properly because we've been born with a polymorphism or a disturbance mutation in the gene, or that particular enzyme is not up to function because it's deficient in a cofactor or coenzyme in order to activate the enzyme to get it to work. Okay? So the first thing you've learned is that enzymes are proteins, and that proteins are expressions of the gene. There are 3,870 enzymes in the database, but that was a few years ago, probably now. I haven't got an up-to-date figure on it, but there are more than that now. And of course, in biochemistry, we're learning about new enzymes all the time, and new biochemical processes that occur, which in older biochemistry books, when we look back in texts of 10 years ago, it looks quite archaic in comparison to these days with the growing knowledge. So every year things are a little bit different. We were talking at breakfast whether, maybe later in the autumn or next year we'll run another seminar, perhaps like a similar sort of filming one on hormones. And Jill said, well, you did one of those a couple of years ago. But a lot has happened in the last couple of years. And a lot of new products have been developed, and a lot of new ideas about enzymes and genetic function have materialized. So every couple of years, we like to update our seminars. Now, there are two types of enzymes. There are those that require coenzymes, and these are such as oxidoreductase enzymes. So an oxidoreductase enzyme means it receives an electron and it loses an electron. And when you add an electron to something, it's called reduction. When you lose the electron, it's called oxidation. So you might want to just make a note of that, because oxidoreductase enzymes work both ways. Oxidoreductase enzymes can add an electron and they can lose an electron. And if they add the electron, it means it's being reduced. And when they lose the electron, it becomes oxidation. So these enzymes work both ways. And this is important. And most oxidoreductase enzymes in the body need an electron transport from a metal or cofactor, as we'll see, which is going to be either iron or copper, because iron and copper have two valencies. Okay, so you always use iron or copper in oxidoreductase enzymes. About a quarter of all known enzymes require coenzymes to function. Now, a coenzyme is a substance that becomes part of the biochemistry of the equation. It donates something into the equation. It might be an electron, it might be a phosphate group, or it could be adenosine, as we'll see. It donates something actually to the two compounds that make up the equation. And the second type of enzyme are those that do not require coenzymes, such as digestive enzymes. So all digestive enzymes don't require coenzymes to activate. Now, a coenzyme, generally, the best way to remember this, is that coenzymes generally are activated vitamin Bs. Most vitamin Bs, not all, but most vitamin Bs are inactive. They're inert substances, and they have to be activated or changed into their coenzyme to actually be able to work in the body. So an example of this would be folic acid. So folic acid has no function at all in the body. It has to be methylated or changed into different forms by the addition of carbons and hydrogens to get it into their active forms. So methyl tetrahydrofolate is an active form, tetrahydrobiopterin. These are all active forms or coenzymes of folic acid. So generally speaking, coenzymes are activated vitamin Bs. The only exceptions to this, and you might write these down because this is a very important quiz question, okay, which you will be asked at the end of the day. Okay, the exceptions to this is vitamin C, or not the exception, the addition is vitamin C. Vitamin C acts as a coenzyme because it receives electrons and donates them. That's why it's an antioxidant, because it becomes oxidized and then it becomes reduced and it recycles itself. S-adenosylmethionine is a donator of methyl groups. SAM for short, S-adenosylmethionine is a coenzyme. S is S for adenosylmethionine. Okay. The next one is alpha-lipoic acid. Alpha-lipoic acid, very important substance. We'll be talking about that a little bit during the day. Has a number of functions in the body. But one of the great things about alpha-lipoic acid is it contains sulfur. And sulfur has a valency of 2, 4, and 6, which means it can reach out and grab various things and detoxify. One of the things it does there is it grabs hold of toxic metals in the system. So it's the nature's own way, the body's own way of detoxifying toxic metals. So when alpha-lipoic acid shows up for a person, always think, aha, I wonder if this person has got an overload of toxic metals. And the fourth one is coenzyme Q10, which we'll meet in the module, the filming module 4, in the energy pathway. CoQ10 works in the electron transport inside the mitochondria to transport electrons from complex 1, 2 to complex 3. So CoQ10 is a coenzyme and it's not a vitamin B. Okay? So it's independent. So that's your 4 non-vitamin Bs. All the rest are vitamin Bs. The total number of coenzymes is 20. Now we have 4 DNA bases and we have 1 RNA base, uracil. So what happens is that you have 4 DNA bases and 1 extra alternative assignment, which is uracil, which gives you possibilities of mismatches within the genes, where you can get one base going into the position of another one. And therefore you've got 4 by 5, which equals 20 permutations or mutations that can occur in the genetic expression. These are called single nucleotide polymorphisms, or mutations, SNPs for short. Okay? So there's 4 by 5, which equals 20, and that equals 20 coenzymes. Okay? So in other words, there's a coenzyme needed for each polymorphism. Okay? And this is how we are able to improve genetic expression and to get enzymes to function better by increasing the concentration of the particular coenzyme in the cycle. So a person may require 1 milligram of pyridoxal 5-phosphate, or B6. The recommended daily dose in this country is about 1.8 milligram. Okay? But some people need 50, 100, or even 200 milligrams, massive amount, because they're not able to activate their B6, their pyridoxine, into the pyridoxal 5-phosphate. So the less that they can activate it, the more they need to take the activated form. And this is why some of our patients need vast quantities of particular coenzymes like pyridoxal 5-phosphate or adenosylcobalamin in comparison to what the recommended daily allowance is, which they would normally, if they can convert, would be very, very small. So as long as you recycle the coenzyme, you don't need very much. But if you can't recycle it and you don't manufacture enough and synthesize it into the coenzyme, then you need to take it in a preformed state. So this is usually a genetic reason why people are unable to activate it. So the enzyme functions are those that require coenzymes or activated vitamins and those that do not, like the digestive enzymes. What we do know is that we need cofactors, which are minerals, to activate each enzyme. And these are like keys that go into the lock on the enzyme to get it to work. And all digestive enzymes require zinc. All digestive enzymes require zinc. So one of the first places you see zinc deficiency is in digestion, okay, or problems with digestion. Right from the production of stomach acid through to the pancreatic enzymes, through to the small intestine enzymes. Now, with an enzyme, there are 4 parts. There's the apo enzyme, which is the protein part of the enzyme. That's the sort of string. There's the coenzyme, which is required for the activation of the enzyme, which we'll see. And we have metal ion catalysts, or cofactors. Now, the common cofactors here, which we'll find and you'll see every day with your patients, is magnesium and zinc. Now, 80% of all enzymes require magnesium as a cofactor. Okay, so cofactors are minerals, 80%. And often you'll see kinase enzymes written down. All kinase enzymes require magnesium. Okay, so the first thing you tend to think about when a person shows up as a mineral deficiency is magnesium. And the second thing that you check is zinc. And then you go down your list for iron and molybdenum and copper and so on. Don't go for those first, because obviously go for the big boys first. Go for the magnesiums. And what we'll be teaching you is which types of magnesium to look at and to test for, and which types of zinc. And because if you don't test with the right form, it doesn't work. It's as simple as that. So if you test with one particular compound of zinc, and the person doesn't strengthen to it, you can say, well, they don't show that you need zinc. And that may be completely wrong. It's just that that form of zinc is not that particular type for that patient. So we need markers which will give you fairly definitive results to tell you that a person is deficient in zinc, but to look through at which is the best type of zinc for that particular person. So if in doubt, always think magnesium and zinc, if in doubt. Okay? You can't go too far wrong. If you don't know what's wrong with a person, think magnesium and think zinc. Now, loosely bound metals form in solution. These are activated, usually alkaline earth metals such as sodium. And we know that sodium is mainly outside of the cell as an electrolyte. Potassium is mainly inside. And then magnesium and calcium. And these 4 work together to regulate cardiac or muscle contraction. So when you've got blood vessels which are constricted and the blood pressure has gone up, this is usually because you have high amount of sodium and calcium. So sodium and calcium tend to lead to constriction of muscle tissue. And if that muscle tissue is smooth muscle tissue of the blood vessels, the blood pressure goes up. So it may be that the person's got excess salt in the diet or excess calcium, or more likely a deficiency of potassium and or a deficiency of magnesium. So remember, potassium and magnesium relax. So if you've got high blood pressure, you need to give potassium and or magnesium. And if you've got low blood pressure, you need to think about sodium and calcium. So they're the big boys. These are the electrolytes, as they're called. Now here's a good example of a cofactor, the popular one, which is zinc, which sits right in the middle of the enzyme called carbonic anhydrase. Now all enzymes end in A's, A-S-E. So when you see A-S-E after name, and usually we like to write the enzyme in italics. So when something's written in italics and ends in A's, you know that's an enzyme. And as you've learned, enzymes are expressions of the gene. So in this case, in the enzyme, which is a protein, and proteins are made of strings of amino acids. We see here glycine, we see histidine here, glutamine and so on, the different amino acids in the chain. And then right in the middle here, locking it all together, is zinc. Okay? Now this is an enzyme called carbonic anhydrase, which adds carbon dioxide to water in the body to make bicarbonate, okay, and hydrogen or protons. So the bicarbonate here is secreted by the pancreas to produce a more alkaline enzymatic matter, fluid coming out to help the digestion, and the H plus is gone to make hydrogen plus chloride, which makes hydrochloric acid in the stomach. So this enzyme carbonic anhydrase works in the pancreas and in the stomach. So it has two functions. It makes bicarb and it makes acid, hydrochloric acid, right? And it requires zinc to do this. So zinc is the cofactor. Now zinc will only work here, or this position will only work with zinc as an ion. And you'll see it's not zinc chloride, it's not zinc sulfite, it's not zinc picolinate, it's not zinc citrate, it's zinc. So when a mineral, as we take it in our food or as a supplement, we take in a compound, which is a dry substance. Okay, it's either in the food or the nutritional supplement you take. When you open that capsule up and you put it into water, it becomes ionized, which means the zinc and the chloride or the citrate separate. Okay? So the zinc has a positive charge, the chloride or the picolinate, whatever, has a negative charge. This is called an ionized solution. And that's the only way that you absorb a mineral. You do not absorb a mineral as zinc picolinate goes into the blood as zinc picolinate. It goes in as zinc ions and picolinate ions or chloride ions. Okay? So therefore we have to, in order to build up our minerals in our body, we have to ionize our compounds from our food and from our supplements. In other words, we have to put them into solution, and to ionize them we need to be in slightly acid solution. Okay, so it splits the two parts apart. And of course what does this is hydrochloric acid in the stomach. One of the major functions of hydrochloric acid in the stomach is to divide the anion from the cation, or the positive from the negative, and put it into solution. Okay? So you can see the whole thing of the digestive process, right from the beginning with the hydrochloric acid, is zinc dependent. So therefore the best forms of minerals are always going to be those forms which go into solution, are most soluble. If you have a zinc compound which you put into a glass of water and you stir it and it either floats or it goes to the bottom of the glass, it's not going to do anything different in your stomach. Okay? So there's very little point in taking something which is insoluble. I think you can all agree on that. Okay? So some minerals are more soluble than others, and some compounds are more soluble than other ones in the same family. So for instance, with calcium, generally calcium products are relatively insoluble. But some are soluble. Citrate, for instance, is very soluble. Calcium citrate is very soluble. Okay? Calcium lactate, like we get in milk, is very soluble. Okay? Calcium carbonate is 99% insoluble. Okay? It's chalk, isn't it? So which calcium do they sell in the pharmaceutical, in the chemist shop to you, as 1,000 milligram capsules or tablets, is chalk, okay? Which is almost totally insoluble and therefore totally non-absorbable. So it doesn't make sense. So the first thing you need to look at is, does the compound that I'm going to prescribe for my patient, when I open it up and put it in a glass, does it dissolve? Okay? Now, not everything dissolves 100%, but what will happen is it goes into solution and it'll largely, and if there's a little bit sediment in the bottom, that's called the nature of the compound, because some parts of it will be insoluble. Now, what you then do is to test it, is you stir it up. So let's demonstrate that. Can we come around here, Gary? And let's just do a bottle of water here. So in the bottle of mineral water, you've got minerals. That's why it's called mineral water, isn't it? Okay. So what we're going to do is we're going to put the mineral water here. So this could be a solution of calcium, it could be a solution of zinc, it could be a solution of selenium or whatever you want in here. Now it looks pretty clear, doesn't it? Okay. So what we do is you use a laser now, and you put the laser through the glass. Okay, so I'm now firing the laser. You can see the laser's live here and goes through the glass, through the water, through the fluid. And I'm looking down the top, and I'll tilt it that way so Gary can get a little bit of a view there, and you should see no line through the fluid. If you see a line through the fluid, it means you've got something bigger than the size of an atom, and the laser will pick it up. That means you've got molecules or clumps or colloids in there, which means the substance is not soluble. Okay? So in other words, if you give that solution to a person to take, they simply won't absorb, because you can't absorb a molecule or molecules, you absorb ions or single charge particles, right? Not clumps of colloids or groups of atoms together. So that's the way you test a good product. Okay? So things therefore which are already in solution, aqueous or ionic solutions, are the best minerals to take. Okay? Now they're not always convenient. Some people don't like them. Some people love them. Okay? We find that there are a range of people who can't swallow capsules, okay, because they gag. Children particularly, and a lot of adults, surprisingly enough, can't. And they prefer liquids. Liquids get in much quicker as a result. A lot of people travel and they don't like to take liquids because of the security in the airport and all this sort of thing. Can we have capsules? So we do both a range of both liquids and capsules for that reason. Okay? Now, not everything, as I say, is 100% soluble, but the best compounds are always going to be those that are most soluble. So the best way to take a capsule of a mineral is to open it up and put it into a glass and then add water and stir it. Now, if it tastes disgusting, you can swallow the capsule and then swallow the water. Okay? But what you must do afterwards is to swirl yourself around, okay? So it dissolves in the stomach. Right? Do not take a capsule with hardly any water. I know some people who can swallow a capsule without any water at all. But think what that does to your stomach. You know, and so I always suggest with minerals particularly, and particularly zinc, always take it with food, and iron, same. Don't put those into an empty stomach because they stick to your gut wall and they can give you quite a lot of nausea and set up some inflammation afterwards. So there's an example, carbonic anhydrase, which makes acid, hydrochloric acid, and bicarb in our pancreas there, and is zinc dependent. Now, this will only work, this enzyme, specifically with zinc. Okay? Now, in the periodic table, we have compounds which have similar chemical properties in the same columns. And just below zinc is mercury. Okay? Now, we all know mercury is a bad guy. Okay? Why is mercury a bad guy? And because it can lock onto the same receptor in the enzyme, but the enzyme doesn't work. It's like jamming the wrong key into your lock and it won't turn. But you can't get the key out very easily. Okay? So it messes it up. So what effectively happens is if you displace zinc and mercury or anything else in the same column takes up a position, it won't function. So what do you get if you get mercury displacing zinc in the carbonic anhydrase is you get a dry stomach. In other words, you get a stomach which has decreased or even no acid secretion. And if you get that, you won't absorb your other minerals because you won't ionize your minerals because you've got low hydrochloric acid or hypo or achlorhydria. The other functions, of course, of hydrochloric acid is to activate pepsinogen into pepsin, so you don't start the breakdown of protein, so you get a lot of gas build up, and you get fermented proteins in there. And thirdly, it's an antiseptic. It kills microbes. You pour microbes into an acid, It's to sterilize it, isn't it? Okay, so you don't take parasitic eggs and pathogenic bacteria. So if you decrease the acid in your stomach, then you're more likely to get pathogenic microbes and fungal spores and things getting into your gut. So there's three main functions of hydrochloric acid, and they all revolve around getting sufficient amounts of zinc into the body. Okay. Now the fourth part to the enzyme is something which gives it a super boost. This is like a kick to get it going. And these things are called allosteric effectors. And they modulate the catalytic activity of the enzymes by changing the position and the shape of the enzyme protein itself. So they lock on here and they change then the regulatory site or the function of the enzymes. Now a very good example of this is silver. Now ionic silver, or silver in solution, will lock onto an enzyme called myeloperoxidase. Myeloperoxidase is a very, very important enzyme because it converts hydrogen peroxide in our white cells into hypochlorite, which is like household bleach. So our macrophages and neutrophils in our immune system spray the bugs and tumor cells and anything they want to get rid of with chemicals like hypochlorite or household bleach. So in order to be able to make the household bleach or hypochlorite, we have to convert hydrogen peroxide into hypochlorite. And that enzyme that does that is called myeloperoxidase. And that myeloperoxidase is stimulated by silver. So there is no pathway in the body that requires silver. So silver is not considered to be an essential nutrient to the human body, but it becomes conditionally essential, if you like, in certain circumstances because it can stimulate certain enzymes into activity. And that's how ionic silver, possibly colloidal, but certainly ionic silver works. So it stimulates myeloperoxidase enzyme, which increases the production of hypochlorite, which helps the person get over the infections. And as everybody knows, ionic silver has been used for 400-500 years in order to treat gram-positive bacterial infections. So that's the mechanism of how it's thought to work. So it's an allosteric effector of converting peroxides into hypochlorite. Allosteric effector. Now, enzymes are affected by a variety of physiological processes. One of these is temperature. Now, some enzymes only come into functioning activity at their height, at their peak, when the temperature raises. So myeloperoxidase is one of those. We don't want to produce household bleach when we don't need it. So what happens is the enzyme comes and becomes activated when our body temperature rises up. So if we raise our temperature up 2 degrees C, we'll start to get myeloperoxidase working much better. So this is why we get a temperature when we've got an infection. So it doesn't make sense to decrease your temperature too much because, oh, I feel hot, oh, take an aspirin or something and decrease your temperature, because you then won't activate the very enzymes to kill the bugs off. So the bug will probably last a little bit longer. The concentration of the enzyme, in other words, that gene expression, how much are we actually producing? In other words, how much is the gene expressing itself? And this is quite amazing, we found, particularly with myeloperoxidase and other enzymes which we have markers for. So you find that a person with an infection may only be expressing myeloperoxidase at 10%, maybe 20%, maybe 50% of what they should be. So what our job is to build it up from its low expression to a degree of high expression. Because unless your myeloperoxidase enzyme is expressing itself in a higher degree, you simply won't get over the bug. Okay? And we've seen this a lot through the winter when we had this unusual flu virus, during the wintertime. And that was around this sort of December, January. And it was a different strain to what we've had more recently. It was an old strain of which a lot of people in the younger generation didn't have any antibodies, any memory cells of. So they suffered with it, and it went on for weeks and weeks and weeks and weeks. For one reason, their myeloperoxidase wasn't being expressed. So we had to learn how do you stimulate myeloperoxidase to express itself much better. Okay, enzyme concentration. And then when the flu went, along comes the adenovirus, doesn't it? And that's the more recent one. Adenovirus is similar in some ways to the flu. And sometimes it lays people up in bed, and sometimes they just get a bad sore throat, chest, cough, conjunctivitis, etc. And that likes to come when the weather starts to change. So this is when it likes to hit March time, maybe April, quite a lot of it around at the moment. And there's very specific remedies which stimulate the immune system for adenovirus and very specific ones for the influenza. So enzyme concentrations, how much are we expressing our enzyme? The substrate concentration, well, this is the orthomolecular approach. If you increase the substrate, in other words, the starter substance, are we going to force more of the conversion in the enzyme? So the orthomolecular approach of Linus Pauling would be to give you more and more and more of the substrate. So if you're depressed and you've got low serotonin, they would part in the tryptophan. 1 gram of tryptophan, 3 grams of tryptophan, 5 grams of tryptophan. We would say, hold on, this is an abnormal amount. You're eating the whole of one turkey at every meal. This is not quite right. We want to be able to convert that tryptophan through. So the orthomolecular approach would be look at the substrate, build up the substrate to force some of the end product through. What we would say is, no, let's build up the substrate, make sure we've got enough substrate, but let's open up the pathway with the coenzymes and cofactors clearly to work. Number 4, pH. pH is important. Some enzymes work more in an acid environment and some in an alkaline environment. Okay, we're looking inside the cell now. So outside the cell, all pH is 7.4. Inside the cell, it can range from 1 up to 12 or 13. So we can go from massive ranges of alkalinity to acidity, intracellular. Extracellular, it's always 7.4. So pH is important. Do we have a tendency to be too acid? Do we have a tendency to be too alkaline? Number 5, inhibitors. In other words, things that inhibit the enzyme from working. We talked about mercury displacing zinc. So that's a toxic metal. That's what a toxic metal is. So you've learnt a toxic metal is something that inhibits an enzyme from functioning. So it could be a toxic metal. It could be a chemical. And we're going to be looking at chemicals shortly, such as in things that we eat and things that we put on our skin, like toiletries. Amazing how many things we put on our skin which have profound hormone effects inhibiting hormone function. Cosmetics, toxic metals. And worst of all of them, the most poisonous of everything, is mycotoxins. Mycotoxins are the most worst poisons or most toxic substances known to man. People can die and inhibit function within minutes of being exposed to mycotoxins. So let's have a look at an example here. Is we've got a substrate, and a substrate means a starter substance. Okay, this is your starter substance that you're starting your recipe. So it's like in the kitchen, you're going to get your first ingredients ready. So your substrate is your first one there. Okay, now we want to convert it to an end product or a number of end products. Okay, so we want to make our finished product at the end of the meal. So we start with our ingredients and we make the end product. And by the law of mass action, which means the greater the concentration of the substrate, the more likely we are to push it in this direction. Right? So in other words, the more flour we've got in the kitchen, the more likely we are to have bread as a result. Okay? Obviously, a few things have to occur in between. Okay? So the end products go what we make, and then the process will go the opposite way, because when we've got too much bread, we stop them producing bread, and we allow the flour to build up, so we call a balance or equilibrium. So once you've converted enough substrate to the end product, and you've got your end product, okay, it'll start either inhibiting this enzyme from working, or it'll start to go back the other way to recycle, because we don't want to keep building up more and more loaves of bread in the kitchen. Now, what regulates the majority or all of these pathways is an enzyme. Okay? So we have an enzyme which is the expression of the gene. All right? Remember, the gene encodes for proteins, and all enzymes are proteins, but not all proteins are enzymes. Okay? But all enzymes are proteins, gene expression. And to get the enzyme to function, we need a mineral cofactor. Remember, the most common ones are magnesium, zinc, and then you look at the other ones. Okay? Now, 1/4, if you remember, of enzymes require a coenzyme to function. And these are usually the activated vitamin Bs, except the 4, which I'm going to test you on later on, which is your vitamin C, your alpha-lipoic acid, your SAM, and your CoQ10. Okay? So here we've got an example of NADH. That's niacinamide adenine dinucleotide, or what's called NAD, which is the active form of vitamin B3. It's got an H, so that means it's the reduced form. Okay? Now, the coenzyme here becomes oxidized. In other words, it loses its H and becomes NADH. So it's lost its electron, and NADH is the end product. So this is the oxidized form of NAD, and this is the reduced form. And simply all we need now is an electron donor to put an electron back here, and it recycles itself. So this is why we only need 1 milligram, 2 milligrams, or 3 milligrams of the active ingredient in the body. It's because we recycle. But if we don't recycle for some reason, and we don't make enough of this, then we may need many hundreds or even thousands of times concentration, more than what we get in our diet. So now we've seen mineral cofactors, okay, zinc, magnesium, etc., and coenzymes, which are activated vitamin Bs. Let's take a real live case of this. And now this is an example of making melatonin. Melatonin is a hormone made by the pineal gland and some other glands in the body, and it helps us to become relaxed, to go to sleep. Okay. It's not a sleeping pill. It doesn't make you go to sleep. You become relaxed in order to go to sleep. Okay, so you've got nothing else to do, the brain is quiet, etc., so you just drop off to sleep, melatonin. And it's made from serotonin. So serotonin is a brain chemical which is made in the brain and other systems in the body, particularly the gut and things. It then becomes acetylated to N-acetyl serotonin, and then becomes methylated. In other words, a CH3 is added to make melatonin in the pineal gland. And this enzyme is called methyltransferase because it moves a methyl group from a methyl donor, and it is cofactored by our friend magnesium. So now we know why magnesium helps people to sleep. Have you noticed that with people? They say, oh, I take magnesium. And some people like to take magnesium in the morning because it's an important part of the energy pathway. They feel better, it gives them more energy, more ATP. And other people say, I take it last thing at night because it helps me to sleep. And this is why, because if they're low in melatonin, you don't want to take the magnesium in the morning because you've gone 12, 18 hours before you go to bed. So this is why some people like to take their magnesium in the evening. Okay, so we got the gene expression cofactor there. Now on the coenzymes, we've got S-adenosylmethionine, or SAM. This is one of the 4 coenzymes that's not a vitamin B. And this is otherwise known as the activated methionine group. So SAM comes along here and it makes S-adenosyl homocysteine, which is the byproduct of the S-adenosylmethionine, because this has donated its methyl group to make melatonin. So N-acetyl serotonin is a substrate, melatonin is the end product, which is what the person needs. Magnesium is the cofactor, and SAM is the coenzyme. Now, how do we put this into practice? And this is what functional biochemistry is all about. And it's very, very simple. Okay? And it's the fundamental rule of all functional biochemistry, right the way through every seminar that I've taught over 20 years. A weak associated muscle will strengthen to the required end product. If you need melatonin, you will strengthen to it. Right? So in other words, you require a particular substance, whether it's a hormone, a neurotransmitter, a mineral, you strengthen to it from weakness. Right? We all agree, we're all happy with that. If you strengthen to something, it's because the body requires it. A strong indicator muscle will weaken when challenged with the substrate. Why? Because if the enzyme isn't expressing itself properly and we've got a deficiency of the end product, we will weaken to the substrate because we've got a relatively high amount of it. Okay? It's not necessarily a toxic level, but it's relatively high because we're not metabolizing it into the end product. So in the case of melatonin, we would strengthen to melatonin, but weaken to N-acetyl serotonin as the substrate. So in other words, we're not converting A into B. Therefore, we've got a build-up of A and a deficiency of B. All right? So it's simple, isn't it? Okay? So you strengthen to the end product and you weaken to the substrate. This weakness to the substrate buildup is negated by the mineral cofactors, i.e. magnesium, zinc, etc., and or the coenzyme. So we may need an activated vitamin B or one of the other coenzymes. Okay? So it's simple as that. So what we do is we look at the biochemical pathway. We see the person strengthens. That's where what the person needs. We go back one stage. Okay, one step in the pathway, because some pathways have multiple pathways to obtain the end product. We go back one stage. If the person weakens to the substrate, that's where the blockage is. Okay? Think of it like a river. Okay? We have, where we live in Marlow last year, not this year, but last year, we had tremendous floods. Now, we have a weir in Marlow, no, not in Marlow, we did in the end, because it all got flooded. But in the river has a weir, and what they do is they open the weir up so it drains the river coming in. So the river coming into the weir is the substrate. Okay? The end product is the house down the stream which I wanted to buy, and Jill wouldn't let me, okay? On an island in the Thames, okay? Now, had the weir opened up, then the house would have disappeared. So it was quite a wise decision not to buy that. So the substrate is the river building up, okay? And therefore, what we're looking at, if we're getting an excess of the substrate, in other words, the river's getting too high, it's getting toxic, and so we get a weak muscle. In this case, the river flooded above where the weir was. Okay? So if you open the weir up too much, everybody gets flooded downstream. Okay? So what we're looking for is we need more of the weir to open to get more water, just like a dam. So the enzyme is what regulates it. And this is what enzymes are all about in the gene expression. And we can modulate that. In other words, we can change it and say, not too much, but just enough to get our end product there. We modulate this gene expression by increasing the concentration of the coenzyme and any deficient cofactor, like zinc and magnesium. So that's the game that we would play.